In the last class, we learned big O notation and A212, how we describe the cost of an operation as the input grows. But big O has a subtlety that trips up almost everyone, and today we are going to master it. Consider an operation that is cheap almost every single time you call it, but just occasionally, once in a great while, becomes expensive. If you judged it only by that rare expensive moment, you would call it slow A212, and you would be badly misled. Amortized analysis is the tool that lets us see its true, everyday cost. It is the idea that quietly makes some of the most used data structures in all of programming and 8-1, the dynamic array, the hash table, and 8-1 fast. So today, let us understand how a sometimes expensive operation can still be cheap. Here is what we will understand today. First, what amortized actually means. Second, the exact problem it solves. Third, the dynamic array and A212 are star example. Fourth, why appending to it is cheap despite the occasional costly step. Fifth, an intuitive accounting way to see it. And sixth, how amortized cost differs from worst case. Let us begin. Let us begin with the core definition, because getting this straight makes everything else easy. The ordinary worst case view looks at a single operation and asks, what is the most this one call could ever cost? It focuses entirely on the single most expensive step in isolation. That is often exactly what you want and 8112, but not always. Amortized analysis asks a different, wiser question. It looks at a whole sequence of operations together and asks, across all of these, what does each one cost on average? It deliberately spreads the total work out over every call. The word itself comes from finance, where to amortize means to spread a large cost out over time in small pieces. That is exactly what we are doing here in A212, taking a rare big cost and spreading it thinly across many cheap operations. So the takeaway, amortized cost, is the average cost per operation over a long sequence, rather than the cost of the single worst operation seen alone. Now, let us see precisely which situation calls for this tool, because it is not always the right lens. Amortized analysis shines when an operation is mostly cheap and 8200 well, nearly every single time you call it, it is fast, running in constant time, done in a flash. This is the common case, the everyday behavior. But then, rarely, that same operation becomes expensive and 8200. Once in a while, a single call does a lot of work and takes linear time proportional to the whole size of your data. It is the exception, not the rule, but it is real. Here is the trap. If you describe this operation by its worst case alone, you would call it a linear time operation and treat it as slow. But that would be wildly pessimistic, because that expensive step almost never happens. The worst case here tells a lie about the typical experience. So the takeaway, amortized analysis is for operations that are cheap almost always, but occasionally expensive and A212. Exactly the case where the worst case alone would badly mislead you. Let us make this concrete with the classic example, the one you use in every program without thinking, an A212, the dynamic array. You may know it as an array list, a vector, or simply a global list. A dynamic array holds sequence of items in memory, and its magic is that it grows itself automatically as you add more. You just keep appending, and it keeps finding room, seemingly without limit. But underneath, that room is not infinite. The array has a fixed block of memory. Most of the time, when you append, there is a free slot waiting, and the append is trivially cheap and 8200 cost and time. Until, one day, the block is completely full. Now, to fit even one more item, the array must find a bigger block of memory and copy every existing element across into it. That copy touches every element, so it costs linear time and 8200. It is the rare, expensive step. So the takeaway, a dynamic array appends cheaply while there is room. But when it fills up, it must resize an A212, copying everything into a bigger space in one costly operation. So here is the puzzle. If appending sometimes triggers a full linear time copy, how can we possibly call it a cheap constant time operation? The answer is in one crucial design choice. When the array resizes, it does not just add room for one more item. It doubles an 8 to 112. An array of size n grows to size 2n. It suddenly has as much free space as it had total elements, all at once. And this doubling is what saves us, because it makes the expensive resizes glow rarer and rarer. You resize at size 1, 2, 4, 8, 16, and 80, 01, 12. The gaps between resizes keep doubling. So as your array grows large, resizes become vanishingly infrequent. Now do the accounting over the whole sequence. Yes, the occasional resize is expensive, but it happens so rarely and pays for so many cheap appends in between that when you spread its cost across all of them, each individual append works out to constant time. So the takeaway, because the array doubles in size, its costly resizes become ever rarer, an 8 to 112, and spread across all the cheap appends. Each append is constant time, amortized. There is a lovely intuitive way to see this, borrowed straight from accounting, and it makes the whole idea click. Imagine that every time you do a cheap append, you deliberately overcharge yourself an 8212. You pretend it cost a little more than it really did, and you set that small extra aside as savings, as credit in a jar. Then, when the rare expensive resize finally arrives, you do not panic about its big cost. You simply pay for it out of all that credit you have been quietly saving up, append by append. The cheap operations have already prepaid for the expensive one. It is exactly like saving a small amount from every paycheck so that when a big annual bill lands, the money is already there and the bill feels like nothing. The expense was real, but you spread its sting across the whole year in advance. So the takeaway, picture each cheap operation prepaying a little into savings and 8 hodwa, and that accumulated credit comfortably covers the rare expensive step when it comes. Now let us be careful and precise, because amortized cost and worst case are both true at once, and confusing them is a classic mistake. The worst case statement is honest yes. One single append N8112, the one that triggers a resize N8112, genuinely does take linear time. If you happen to call that exact append, it really is expensive. That is not a lie, it is a fact about one operation. The amortized statement is also honest, and it describes something different, averaged over a long run of appends. Each one costs only constant time. This is a fact about the sequence as a whole, not about any single call. The key is to know which question you are answering. If you fear one specific operation, blocking a real-time system, you care about the worst case. If you care about total performance over many operations, which is usually what matters, you care about the amortized cost. So the takeaway, a single append can be linear in the worst case, yet every append is constant time amortized and 8212. Both are correct because they answer different questions about the same operation. Before we finish, let us see that this is not just a party trick about one data structure, an 8200 tool. It quietly underpins tools you use constantly. The dynamic array is the obvious one. The global list at the heart of nearly every program is fast to append to only because that append is constant time, amortized. Without this idea, it would look alarmingly slow on paper. The hash table is another. As it fills up, a hash table must occasionally resize and rehash all its contents and 8212, a rare, expensive step and 8212. Yet its insert stays effectively constant time, for exactly the same amortized reason. So a great deal of everyday, high-performance code depends on this single insight. Whenever you meet a structure that is fast on average but has an occasional costly resize, amortization is almost certainly what makes it work. So the takeaway, dynamic arrays and hash tables are fast precisely because their rare expensive resizing steps amortize away across all the cheap operations around them. Let us gather the deeper lesson, because it will change how you judge algorithms from now on. First, do not be frightened by a rare expensive step. An operation that occasionally does a lot of work is perfectly fine, as long as that expensive step happens rarely enough to be paid for by all the cheap ones around it. Rarity is what redeems cost. Second, Learn to judge an operation by the right measure. For work done repeatedly, the honest question is almost never, what is the single worst call? But what does this cost on average over the whole sequence I will actually run? That is the number that governs real performance. Amortized analysis is simply the discipline of asking that better question and 212, and it reveals the true, everyday cost that a naive worst-case glance would hide from you. So the takeaway, do not fear a rare costly step. Judge an operation by its average over the whole sequence in 212. That is how you see its real everyday cost. Let us gather the whole class in one breath. Amortized cost is the average cost per operation over a whole sequence, not the worst single one. It is the right tool for operations that are mostly cheap but occasionally expensive. The dynamic array appends cheaply until it fills, then resizes in one costly copy. Because it doubles in size, resizes go rare and 212, so each append is constant time amortized. The accounting view, each cheap step prepays a little, covering the rare expensive one. Worst case and amortized are both valid and 212. They answer different questions. Next class, arrays, up close, the simplest structure of all. One idea at a time. That is amortized analysis and 82012. The art of spreading a rare, large cost thinly across many small operations, so that on average, everything stays cheap. Once you can see it, the growable list, the hash table, and a dozen other everyday structures suddenly reveal why they are as fast as they are. Judge an operation by its whole sequence, not its unluckiest moment, and you will read performance the way an expert does. We will see you in the next class.